So we're going to talk about frequency and wavelength here. And before we talk about that, we have to understand that frequencies and wavelengths are in relation to electromagnetic radiation, and all the forms of electromagnetic radiation can be shown here, and this is called the electromagnetic spectrum. Now, the only portion that we humans can see is this little portion of visible light, but you've probably heard of most of these other types: gamma rays, X-rays, ultraviolet, we have infrared, microwaves, and then of course like TV and radio waves. You do not have to memorize this order. We're going to talk a lot about frequency and its relationship with wavelength, but again, the only portion that you can see is this small portion, which is the Roy G. Biv colors. Now, what is a wave? A wave is a continuously repeating change or oscillation in some sort of physical field. So we draw waves oftentimes like this, and so they have an x-axis and a y-axis, and if you take a physics class, you'll get a little bit more into this, but we just have to understand that light is a form of electromagnetic radiation, and it moves as a wave, so it oscillates as it travels through different fields in space. So when we talk about wave, there are some properties of waves we can learn to calculate here, and the first one is wavelength, and it's going to be symbolized by this lambda, and I draw this lambda not as fancy. I kind of just go ahead and draw it like that, so you're going to see that a lot, and that is the distance between any two identical points on a wave. So I'm going to go ahead and go below just to show you what that is. So you can either pick the tops or you can go ahead and pick the middle portions, but this is a wavelength. So again, you can do that on any point as long as it is the same location on two waves. Okay, so that is wavelength. And then frequency is, we use this nu, and I just usually write that as a V, and is the number of wavelengths that pass a fixed point in a certain unit of time. So it's basically like how fast the wavelengths are going past in a certain amount of time, and we'll talk about that a little bit on the next slide. Now, the unit for frequency, there's a couple units you're going to see. Very common ones are 1/2 or seconds to the -1, and you know anything to the -1 is basically the same as saying 1/. And then we also call this hertz, so 1/2 seconds or seconds to the -1 can be called Hz or hertz. Any of these units are perfectly applicable. Now, wavelength is oftentimes in meters, which we know to just be in M. So let's talk about the relationship between frequency and wavelength. So again, I'm telling you that a short wavelength you can see here by having a shorter line in between the two locations you've picked, where a long wavelength you can see here on the same 2 points. Now, frequency is, again, how much is kind of passing through a single point. So let's say I went ahead and drew a box, and let's say I'm drawing the same box on both of these, and let's say we set a timer for a minute, and they were moving at the same speed, then the amount of waves that would pass by in the one that on the top would be a lot more, right? If 1 minute was passing for both of these. So because of that, that means that it has a higher frequency. So frequency is how often we're seeing a wave pass by in a certain amount of time. So high frequency has a short wavelength. So this is a relationship we want to work on here and understand. When something has high frequency, it means it has a shorter wavelength. That means it can move a lot faster. Now, low frequency means it's not as many waves pass through, is due to a longer wavelength. So we call this relationship, one increasing, the other decreasing, an inverse relationship. Okay, so we can go ahead and say, we're going to use this relationship a lot, that wavelength and frequency have an inverse relationship. As one increases, the other decreases. Now, if they were both increasing or both decreasing, then we'd call that direct, but we're not. We're talking about one increasing, the other decreasing. So high frequency, shorter wavelength; low frequency, longer wavelength. Okay, and you can make predictions based off of this relationship. Now, we can also do calculations with these two variables here. We have, again, frequency being shown here, and we have it being multiplied by wavelength. And then something that you're going to be given is c, which is the speed of light, which is 3.0 times 10 to the 8th meters per second. And remember, when we see it written like this, it's the same as having it as a numerator and denominator unit. Now let's just go ahead and check out our units as we want to get used to doing in this course. So if this unit answer is meters per second, and we know frequency is 1/seconds, and we're multiplying it by wavelength, which we need to be in meter, so this makes sense. Meter would be on the top here, and seconds would be on the bottom, and we would end up with meters per second. So doing the math with the units and getting more comfortable with that is something that I really am trying to push in this course. Now, the issue is visible light, the portion that we can see, is oftentimes given in nanometers. And you will have to know this conversion, and I will show you some examples as we go through here. So 1 meter is equal to 1 times 10 to the 9th nanometers. Nanometers are really, really, really tiny. So before you can put this into the wavelength part of the equation, it has to be in meters for this unit to work, okay? So it has to be in meters, and this one has to be in hertz or 1/seconds, or seconds to the -1. So again, let's talk about that relationship, and we can see the relationship here in the way that it's written. So let's say our speed of light is which it always is going to be, 3.0 times 10 to the 8th meters per second. So if we would increase our frequency value, then to keep this number the same, the only way, since they're being multiplied, is you'd have to decrease this number. So again, as one goes up, the other goes down. We call that an inverse relationship. Okay? Now let's go ahead and do some math here, and you will be provided with this equation here, and you will be provided with the speed of light always. You do not have to memorize either of those. So we're looking at here, what is the wavelength? So we are trying to find this lambda of the blue light with a frequency of 6.4 times 10 to the 14th seconds to the -1. So again, frequency is the V. So we're going to go ahead and plug in our V. We are looking for this, and we know this C value to be shown here. So I'm going to go ahead and show you what that looks like. I wrote that out just to save us some time here. So we have the speed of light, meters per second, equals my frequency times wavelength. I'm going to divide both sides by the 6.4 to get the lambda by itself, and then my answer ends up being in meters, and usually this is to the -7th power. Frequency is often to the 14th power. So a couple little good things to keep making sure that you're doing this correctly. All right, so we're going to go ahead and try another example here. We're looking for now this time frequency, and frequency is the V, and we are given a wavelength, which is the lambda, of 6.81 nanometers. Now, first issue here is that it is in nanometers. We cannot have nanometers in our equations. So what we're going to have to do is first convert. So I went ahead and took 6.81 nanometers, and I went ahead and did the metric dimensional analysis that I've showed you before. So nanometers on the bottom to cancel it out, meters on the top. We know there's 1 meter in this many nanometers. You have to memorize that. Now what I like to do is just write it like this and not put it in my calculator. I just take the number, and when you're dividing by an exponent, it just becomes negative. So I like to write this as 681 times 10 to the -9th. But if you do this in your calculator, you'll get 6.81 times 10 to the -7th. These are exactly the same thing. These are exactly the same thing. So it doesn't matter which one you choose as long as you've done it correctly. So it's always good to use a calculator if the top one doesn't make sense to you. Now that I have it in meters, I can go ahead and utilize my equation here. So my equation is C equals lambda times nu. And again, I can use that speed of light. I can use my solved for meters and multiply it by the frequency I'm trying to find. I'll go ahead and divide and make sure I get my answer shown here. Again, your units can be hertz, or you can do 1/seconds, or you can do seconds to the -1. It's whatever works for you. Again, you have to memorize this conversion factor. Now we're going to go ahead and talk about kind of the discrepancy when they were first discussing waves. They said, does it move as a wave, an oscillating wave, or does it move as a bunch of particles? And this was a great debate in the early days. And so initially scientists thought matter was comprised of particles, and then they thought energy was made up of some sort of waves. But there were certain issues with those ideas. So Mr. Einstein came along with another scientist, Max Planck, and he actually described that energy had both wave and particle characteristics. And so he discovered energy is in little packets, little forms of what we call photons. And so we call them quanta photons, which is just a quantity of certain small packets of energy. And we know energy to be in the units in this course of joules. So that's just kind of trying to paint this big picture here for you. But the big thing here was it was discovered that light is a stream of photons and also has wave properties. So although it's kind of moving in a wave pattern, it is made up of particles. That's kind of how I imagine it. So it oscillates, but is made up of tiny particles. Now from this math, we are now introduced to a new equation here, E equals H times V, and that V is the same frequency we've used before. And we are introduced to a new constant, and that is H. We call that Planck's constant, coming from Mr. Max Planck. And this number is very, very small. It is 6.63 times 10 to the negative 34th, and the unit is joules times seconds. And so energy here, let's go ahead and again kind of work through our units. So if this is a joules times second, and this frequency is a 1 over seconds, then we will cancel our seconds out, and our energy unit will end up just being joules. Okay, so you need to make sure you know the units for these as well. Now from this, Einstein then could kind of put together a new thought, and this is a really gigantic concept in terms of waves. It is called the photoelectric effect, and there are tons of videos on this. I will try to find one and post it. The photoelectric effect is the ejection of an electron, so from the surface of a metal. So this is a metal. Okay, we could say it's copper, we could say it is iron, whatever. And we have these light rays, which we are going to in this class called photons. And photons are just little packets of light energy. And so as the lights are coming in, again, this could be sunbeams, they are hitting the metal, and what's happening is the electrons are gaining the energy. So these photons are actually forms of energy. And so they are gaining the energy. This is me showing energy being gained, and they get so much energy that they need to move, and what they do is they actually eject, literally leave the surface of the metal. And so this just shows how energy is transferred from this form to then being ejected out of this. Now, all of the ejection comes from the frequency of these waves. So smaller waves, larger waves, has a different effect on the metal type. Basically, you just have to understand energy as it hits a metal, the electrons gain energy and are ejected. Now from this, Einstein used this understanding of light to explain that photoelectric effect, and that was in 1905. Again, you don't have to memorize dates here, but it just kind of puts it into perspective. And he learned that each electron is struck by a single photon, and remember, we can kind of think of it as like an energy beam from the sun. And when that photon of light has enough energy, the electron from the metal will be ejected from the atom, and that photon is said to be absorbed then by that metal. Now, because of this experiment and these results came this really large concept in chem called particle wave duality, and that basically is when as I kind of described before, the wave moves in an oscillating wave-like fashion, but also is made up of particles. Now we're going to go ahead and do another type of example, and this is the last type of example with these two equations, and you are actually going to have to very often use both equations when you are calculating things here in this chapter. So a blue-green line of hydrogen, of the hydrogen atom has a wavelength of this. So we are given a wavelength of 486 nanometers, and again, we see nanometers, we need to convert that to meters. What is the energy? So our plan of attack here is we are given nanometers, which we'll convert here. So we will first use that, and we will use our speed of light, which we have here, and we will then solve for V. When we solve for V, or frequency, we then can use this equation, because the whole goal here, what we're trying to find is this, okay? That is the energy. We're trying to find this. So we can then go ahead and use our frequency we solved for, plug it in here, use our H value, and then solve for the energy. Okay, so this is a couple-step problem. So you have to first do this equation and then go ahead and utilize this equation. And again, all of these are given to you. So you can see here in step 1, in purple, I converted from nanometers to meters, and again, you can go back if you don't recall how we did that, just using your conversion factor. And then I went ahead and used this first equation as I described, C equals wavelength times frequency, or frequency times wavelengths, doesn't matter. I used my speed of light and the meters of the frequency or wavelength I solved for, and I solved for frequency, again, making sure that it is in the correct unit. I then went ahead and used my second equation, E equals H times V. And again, I have that H value because it is a constant. And I used my frequency, plugged it in here, multiply these two values, and went ahead and found my answer of energy in joules. Now again, energy is typically to the negative 19th power, negative 20, sometimes the negative 18th.